Happy to be the last one from CelePixel. So we are based in Shanghai. I'm also affiliated with Nanyang Technological University, Singapore. So this company, in fact, is spin-off from the university. Our sensor is branded as Celex. Seller probably know that in Latin means fast. So we know that the event-based sensor, since the day it's born, we believe that it had low latency, so it can boost the response time of the vision system. So that's why we named our sensor with this. So very quick review. Comparison between event-based sensor and frame-based sensor. So to me, in my opinion, the main difference is that conventional sensor, the frame-based sensor, is passive. So there is an array. So after exposure, so whether it's a global shutter or rolling shutter, so they always scan all the pixels. So if there is no change on the pixel, but from the outside, you don't know. So you still read all of the pixel out. So in this case, you will have a lot of redundant data. But for event-based sensor, so every pixel, you have an event generator. So only there is the event, so the pixel will be read out. So in this case, we can reduce the redundant data and also increase decreased response time. Okay. So this is basically the history of our sensor. We have the prototype come out in year 2011. Then later in the year of 2015, we spin off company in Singapore. By that time, we have resolution of 380 by 320. And then in 2017, we moved to Shanghai. And then we have a 500,000 pixel sensor. So among the few startups, we are the first one to have a 1 million pixel sensor. So which has this 1280 by 800. Also, this sensor is automotive qualified. So we pick up a foundry that can do this had automotive qualification process because the main application we look at now is automotive. So currently we have around 40 employees, and some in Singapore and some in Shanghai. So now let me introduce the main difference between our sensor and a few other friend companies. First, we introduce a new kind of event packet. So instead of this XYT, I believe the people sitting in this room understand what that XYT means. Or XYPT, P means polarity. We provide a new event format called XY80. So A could be two types of data. One is that it could be in pixel time step. And then it also could be the pixel's logarithmic grid level value. So it means that when the pixels are fired, when the pixel you read out from outside, you immediately have its grid level value. You don't have to do an extra exposure time. So in this case, it's a grid level value, and it's this event time step are closely correlated. So we understand, today there are a few works trying to reconstruct the image. So in our case, you don't have to do that. It's already offered to you. So we believe that this can bring a lot of advantage. Because we know that in order to do tracking, you will need a motion model. So in which XYT will be enough. So with XYT, you will be able to track object. But if you want to identify or classification on some object, you need its appearance model. So can we do it together? With its both spatial and temporal information. So we believe that our event packet can do this. And also, we believe that with this in-pixel time step, it can provide accurate and free of readout jitter or delay. So we know that for event-based sensor, its main operation principle like this. if you have some pixel, whether you have some motion or not, some object is there, the pixel are fired, and then later, by rule or column handshaking, the pixels are read out one by one. So usually, we assign a time step. So basically, in the chip, there is a global counter. It works as like timer. So when the events are read out, you assign a time step to it. So let's say if you have a big object. So for example, the object occupies 10% or 20% of the whole scene. So in the real case, all the pixels should have the same time step because they move together. They belong to the same object. However, due to the readout delay, and also there is some randomness. So, when the pixel fires, you have no idea which one will be read out first. It could be this rule first or this rule first. So when they come out later, then you have some delay. So in the worst case, for example, if you have all the pixels fired, and the time it takes to read out all the pixels is long. For example, if the readout speed is 100 megahertz, so 10 nanoseconds per pixel. If you have 1 million, that will be 10 milliseconds. So it means that you will have a jitter or delay, so in between 0 to 10 milliseconds. So it will be big. So in this case, the time event, the time step will not be accurate. And also it changes from time to time because there is jitter, because there's some randomness inside. So using this in-pixel time step, we can solve this problem. And the third point is that in our sensor, we build an in-pixel optical flow. So therefore, in summary, our sensor provides a new kind of event packet. We can provide the global shutter, grid level pictures, and also we have this in-pixel time step. So basically, this is the new feature that we bring to the community. So this is the specs of our 2nd-generation sensor. This is the one we designed in 2016. This one is available since last year. The pixel size, our newest generation is 9.8 by 9.8, and also it's automotive qualified. The latency, of course, we just understand from uncertainties. So in fact, this latency we talk about is the electrical latency. It does not include the conversion time from the light to photo current. Okay, and then the output signal are already introduced. So it's 3 kind of modes. So we can do automatic looping. After you do configuration, you don't have to care. They can do automatic looping between the 3 modes. Okay, so let me introduce to you. So how do we do this? Of course, this part is mainly on hardware, but I try to explain it so that the people working in software can also understand. So the pixel structure can be grouped into a few parts. The first part is log photo detector. So this part, the main difference between this part to conventional like what we use in our cell phone is that it takes no time to do the conversion from light to signal. Okay, it's do like an always-on kind of sensor. Whenever you have some photo current, you will have a corresponding voltage. Okay, the second part is the ripple detector. So when the light is constant, there is no change to this voltage. However, when you have some turning to bright or dark, you will have a detector here to detect whether the change is big enough. And then in our case, we don't care whether you're changing from bright to dark or dark to bright. We add them. Okay, and later when we have internal memory, so when the pixel fires, so what we do that the data will be sent out. So we also have on-chip something called ramp voltage. So this one will be act as like an analog time counter. So I will talk about this part later. So also in our chip, we from the previous generation, we have discard something called AER, because we found AER bringing a lot of problem. It bringing a lot of randomness, okay, and also data. So therefore, in our sensor, we use a kind of a new scanning mechanism. Okay, it works. I mean, the efficiency will be similar to AER, but its behavior is very different. And as I said, in order to deal with jitter or delay, we have in-pixel time step. Also, the readout speed is high. Okay. Okay. So this is the signal path for these digital events. So when we have some ripple, here are some handshaking circuits will send out some sparks outside. And then there is some post array time step. This is similar to conventional XYT format. Now, how about XY80? So this first, this gray level value. We said that we can provide this time step and also this gray level value together. So how do we do it? So when the pixel fires, you introduce the event, and at the same time, we are going to send out some signal here. So this signal will activate another in-pixel memory. So this memory will sample this voltage to here. After that, when the pixel is selected, so this signal will be read out to the column bus. So what did this signal? At the beginning, I said this detector is a logarithmic detector. So which means that this voltage is directly related to its brightness. Okay, so therefore you read out this voltage, you will know what the pixel look like. You will have its brightness value at the same time with the event. So it takes no time to have it. So in this case, the two information are closely correlated. And then we have another signal with something called force fire. So this signal has nothing to do with the event mode. So you can see that once we introduce some kind of external signal, so we are going to force the pixel to be fired. So in this case, we can turn on this switch. We can force it to turn on. Okay, we can sample this signal to this detector. So in this case, we can get a global shutter picture. Okay, so therefore, how come we can also capture conventional picture in a global shutter way? So now come with our capability of in-pixel time step. So what we do that, for example, you have two-car crash, okay, at high speed. You want to have a very accurate time step for the pixels. So what we do that when the pixel, begin to work, we provide a ramp voltage. So this voltage, changes from low to high and takes some time. When the pixel fires, we are going to sample this voltage into the detector, into the in-pixel memory. Okay, so the time of hit happens will be correlated to this voltage. So different time will have different voltage. So later, when the pixels are selected to read out, we are going to read out this voltage. Of course, you know that this voltage, in fact, corresponding to its time. And in this case, we don't care how much delay or how much jitter. Okay. Now, so here it gives you some sense of what's the benefit of in-pixel time step. So we have a rotating, spinning kind of plane here. There are 3 bars here. So this is the time step. This is this 3D point cloud. This x, y, and this dimension is t. So you can see that with this off pixel or conventional x, y, t format, so the plane you have will be kind of distorted because this event is generated the time step. Basically, the time step will be distributed within some range of time. Okay, and then using this in-pixel time step, you will have a very good slope, very good time surface. Okay, and this is this accumulated picture. We just take a very small time slice, only 20 micron second. So we can also have a very good shape of this these bars. Another capability of is on-chip optical flow. So this also leverage this in-pixel capacitor and also ramp voltage. So what we do that we have a start signal. Okay, we see that we start to do optical flow. In this case, we let the ramp voltage to run only once. So what happens is that so you can imagine that you just imagine this in my pen. So my pen begin to move. The first pixels fired due to the motion of my pen will have some voltage of here. The second part of motion will have basically, for example, this voltage. And then the voltage will be higher. So what do you have? You think about this the value we recorded on this capacitor. What do you have? You will have this kind of like a surface. Okay, the slope, the direction of this slope will be the direction of the pen's motion, and this angle, basically the slope, will related to the speed of my pen. So what we do that, we read out all these values of this capacitor. We will have this kind of time slope surfaces. We just need to extract its slope and direction. Then we will have its optical flow. So I believe some of you already see the demo of the sensor, and later if you wanted to look at it again, please let me know. So the sensor is with me. And then the application of the sensor, we believe it can be very wide. As long as you wanted a fast response, and then you cannot have a very powerful computer, then you will have application there. At the moment, we are focusing on automotive because we found out we can really solve some pain points of this automotive in this automotive area. So with this special capability of a sensor, we propose kind of hybrid processing because we know that currently purely event-based processing, we are still not there yet. There's still some gap. So can we try to leverage the all the different data format and try to improve the efficiency of this system? So we can use some full picture functions, event mode data, and optical flow. So we can do this in the time domain, do a loop. So the first mode is full picture, and then you have the second mode. It can be a soft optical flow, or either this green pixel value, in the format of XYT, and later you have hardware optical flow. So each of the mode you can assign a 10 millisecond time slice to it. So in total, one loop takes 30 milliseconds. So therefore, 1 second we can do 30 times of this looping. And here show you some demos we did in the company. It's mainly for automotive. This one is lane detection. You can see that we can do pretty well. The blue color is the detection result, and the yellow color is tracking result. And this is bird view of this lens. Okay. We can also measure the distance between the lens. This is what we did with sensor fusion. This kind of event-based sensor with radar. So some automotive makers, they believe that this combination of vision sensor plus radar sensor can replace LiDAR, because many of the automotive makers, they don't like LiDAR. Okay, and we already do a very good demo. So for each of these red reticle is the result recognized by the sensor, by our sensor, and there is a blue dot. The blue dot is the result by the radar sensor, and then we do a fusion. And this side is look at the speed of each vehicle. You can see that it's very much stable. If you only using vision sensor, there will be some kind of flicker, because on the road, sometimes there could be a small piece of rock, or there are some kind of something is not flat. In this case, the distance will have a sudden change, because the optical kind of relationship does not work anymore if the surface is not flat. And this is the human tracking. This is vehicle detection and the tracking. Again, blue color is the detection result. Red color is this tracking result. Okay. The other side is human detection and tracking. So all these competition is what we did is a hybrid processing. We use the optical-flow to do tracking, and then using this full picture mode to do recognition. Okay. Also, we are working with Wuhan University to do visual SLAM. I'm not an expert in SLAM, so I cannot comment how good. Probably Jaime can comment. Okay, this last page is similar to like in science. We are also hiring anyone working in the AI or computer vision. So you're welcome to contact us. We are based in Shanghai and also Singapore office. If you want to sample, you can also contact us. Basically, we have two types of interfaces. One is this sensor interfaced to MIPI to USB conversion chip, so that you can use USB cable to collect data. Another one is that if you wanted to do embedded processing, so we provide a FPGA SoC solution. This, in fact, is a Celex Sensor. Part of the chip is FPGA, part of the chip is CPU. So it has a Linux inside. Also, it comes with Ethernet and also a high-speed serial link. Okay, thank you.